Good morning, everyone. Welcome to week 9 of MATH13218 Advanced Application of Mathematics. Today, we'll be talking about some mathematical modeling and solve some questions based on modeling. It's kind of tricky content. Modeling is a bit tricky. So you have to bear all the knowledge that you acquired so far and then use that technique of solving differential equation into mathematical modeling. Okay, let's begin. Right. So this is how a mathematical modeling looks like. So what we got here, we got a physical system, like our day-to-day lives thing, right? We start here. Any physical system, any real-life situation, right? If you could recall in an earlier maths unit, we are talking about height and distance problems. So there were similar physical system, practical or real life situation, and then we convert that into mathematical equations, mathematical modeling, and then solve it using mathematical tool. And that mathematical tool or the response or the solution doesn't make sense. So we convert it back into the real world or wording that an end user can understand. Another example of this when we are talking about solving system of linear equations, where you have more than two or three variable, and then couple of situation. It could be the circuit I1, I2, I3. It could be number of coins. It could be asset distribution, many such things. It could be vectorial growth, decay, either exponential, increasing or decreasing kind of situation, population growth, another example. So all that kind of physical world or the real life situation. Then we form a mathematical model from it. Once we got the model, using some data and all this thing, we go for the mathematical solutions of it, right? Um, and then the solution should make sense. Sometimes it may happen that the solution is not correct. So whatever parameter we would have tried doesn't work out. Then we change the parameter, right? So if the physical interpretation doesn't make sense, we change the parameter and come back to the mathematical solution. We do the same thing, right? That modeling stays the same. The equation that you formed the same, but it's that the initial condition or the things that we have assumed doesn't work out the way we thought, right? And if everything works well, then we go for simulation of how it looks like using graphs, testing scenarios. And if that works well, then we provide the outcome, right? That's all thing. This everything up here is called the modeling, and this part here is called testing or simulation. Okay. Right. Okay, so we have three special cases that we will discuss today. One is the motion scenario. The next one we will talk is this mixing problem, mostly salt water, where there is some salt concentration where you are replacing, like salt doesn't mean just one salt. It could be any chemical salt, right? There's many chemical salts out there, right? So you are reducing one type of salt and increasing the concentration of another type of salt, right? So they are all mixing problem, physical and chemical system, right? This is the second situation that we'll deal with. And finally, the third one, we'll talk about spraying a fruit tree with pesticide. So again, here is a system of linear differential equations. So we'll look at them as well. Okay, cool. Let's go back to case one. Right. So a train is moving along a horizontal track. Right. So this is how the train is moving a horizontal track. If a mass m and the pulling force or attraction is F. Now, most of the situation, you'll be given all the required formula, but if it's some basic formula, like for example, F is equal to ma, all that kind of thing, then you should be familiarized. You should make yourself familiar with certain basic things, right? Okay. The resistance R is given by A plus BV, where A and B are constant. V is the speed of the train. If S is the distance traveled, find S of t. So distance as a function of t with the initial condition S of 0 is 0 and V of 0 is 0. If the initial condition are not given, then your answer will contain some constants. In order to remove the constant, we should be given some particular conditions, right? Right. Okay, so we need to form a differential equation from here. We are given V, right? Yeah, the basic relation, if you say not this A, the acceleration A is dv by dt, and we know V is equal to ds by dt, and we have F is equal to ma, right? Now the resistance is also a force as well, right? So we start with F is equal to ma, right? In this instance, since there is a resistance, right, the output or the resultant is F minus R is equal to ma, right? So there is this mass M, right? It is having two forces in effect, F and R, two forces in effect, right? We replace the value of this, and we replace this A as dv by dt, right? So F minus R, which is A plus BV, is equal to M dv by dt. Remember, our aim is to form a differential equation from here. And therefore, M dv by dt is equal to F minus A minus BB. Or we can write in a differential equation that makes sense to us and is easy to solve, right? We can divide by M. Okay, so dv by dt is equal to 1 over M. We keep the constants away, and 1 over M. We keep it, the V term on the left hand side. So dv by dt plus B over mv is equal to 1 over M F minus A. This is similar to our Euler's equation, which we have covered in week 3, I believe, or week 3. Yeah, week 4 was numerical solution, right? Okay, so if we, like I said before I started, you need to be familiar with the topic we have covered, so it will increase your understanding. So this is your P, this is your Q, right? So P of T is B over M, and Q of T is 1 over M F minus A. For our convenience, we assume this as capital A and we assume this as capital B, just for our convenience, right? So that way your integration and all that part becomes a lot easier. You can do that. I mean, you are not replacing the variable. You are just like C1 plus C2 plus e raised to C3. We call it constant C. Yeah, so as long as a constant is there, you can always rename it as per your convenience, right? So this differential equation would like dv by dt plus av is equal to b. And I'm sure you will agree, this is a lot simpler representation than what you are doing here. It will help you with integration and all that part. And once you are done with integration, you put it back, right? Remember, a and b is your assumed variable. We have to replace it back, okay? So we follow the same solution system. First of all, we start with mu of t. You know, you can solve this equation by any different means, right? So here I will use this mu and p and q approach, right? Maybe with the other example, I will go for that homogeneous, non-homogeneous part. That should all give the same answer, right? Mu of t is e raised to minus p of t dt. P is a up here, so e raised to minus at, right? Okay, then we go for our v of t. The solution is equal to mu of t c plus integration q of t divided by mu of t dt, right? We replace the value of q and mu. So our v of t will be e raised to minus at c plus q is nothing but b, e raised to minus at c. B can stay outside. E raised to minus at is in denominator. You take it up, it becomes e raised to plus at, right? Its integration is 1 over a, yeah, e raised to at. Okay, right. We multiplied inside, so c e raised to minus at plus b on a, because e raised to minus at and plus at is cancelled out. So this is our v of t. Now we substitute back our a and b, right? Set for your v of t. C is the integration constant. A, what is our A? A is b over m. B is f minus a over m times by a, which is b over m. So this is 1 over a becomes m over b. We simplify this, okay? So your v of t, we leave the constant in the front, so it's easy to see. F minus a over b plus c e raised to minus b over mt. This is my v of t. In the original constant, a and b and f is a standard one, right? C is the integration constant. Now, remember we are given some initial conditions. We are given some initial conditions, right? So this were the initial condition. S of 0 is 0 and v of 0 is 0. We will use that, right? So first of all, our goal is to find S. So first we will start with V. We will find V. V is again, as we know, ds by dt. We'll integrate it once. And then again, we will have something S with integration constant. We use the second initial condition to find our S. So once the model is set, is all integration technique, differential equation solution technique, and that shouldn't be a problem, right? Okay, so we replace the initial value when t is 0, your v is 0, right? So 0 equals f minus a over b or over m, yes, b, plus c e raised to 0. This will give you c is equal to minus f minus a over b. So our v of t is free of the integration constants. So f minus a over b minus f minus a over b e raised to minus b over m and t. Right? If you wanted to make it look simplified, we got this as common 1 minus e raised to b over m and t. This is my v of t. Our aim is not to find v, our aim is to find s. So what we will have to do is an integration of this given one. Okay. Therefore, v, which is ds by dt, is f minus a over b, 1 minus e raised to b over mt. And therefore, s is integration. So f minus a over b, integration of 1 is t, e raised to minus b over mt, multiplied by minus m over b, right? Plus some constant c. I call it C1 because we already used C earlier, right? Why did we get this? Because the multiple of t goes in denominator, so minus b over m goes in denominator, so I simplified that. Okay, so my S finally will be f minus a over b, right? T minus minus plus m over b, e raised to minus b over m, plus some constant C1. Now I'll replace the second initial condition. When T is 0, S is 0. So 0 is equal to F minus A over B plus M over B plus C1, right? And therefore, my C1 will be minus M F minus A over B square, okay? And therefore, my S will be, we replace it back here, F minus A over B T plus M over B e raised to B over mt minus M F minus A over B square. Right, and then you can keep on simplifying it until you are satisfied. So what we do, F minus A over B is common, we keep it outside. Inside is T plus M over B e raised to minus B over mt, and over here will be minus MB. Again, as we can see, this both has MB, 1 plus M over B, right? E raised to minus BT over M minus 1. This is my S, right? And then you can go for, um, you know, validating this model if that's, you think you should, right? So that's your S, right? So again, let me quickly review what we have done. So train is moving along the horizontal line, mass is M, pulling force F, R is given A plus BB, A and B are constant. Whatever constant from the question, you can always keep it. Anything else that you have added should be replaced back, right? S is the distance traveled, S of t, that's what we are looking for with two initial condition. The only assumed knowledge is A is dV by dt, the acceleration, and therefore V is equal to ds by dt, F is equal to ma, right? These are three very basic, like literally very basic science concept that you should remember. F is ma, so the actual force acting on the body is F minus R is ma. Replace the R is equal to A plus BB, and then you keep on solving it. So you got a differential equation here. That's your differential equation. And once you got the differential equation, then you use any of the learned differential equation technique, make it a nice differential equation, non-homogeneous. You can go for your P or Q approach, mu of t, V of t. Now, this is all integration that we'll learn. You got your V. We replace the initial condition to get rid of the integration constant C. This is something that we have to change, right? Find the value of. Therefore, once we do that, we have our V of t. V is again ds by dt. Integrate it once more. You got some other constant C1. You could have called C, but I just called it C1. Just to make it different from the other one, because otherwise what will look like over here, you got the value of C as this, C is this one, minus F minus A over B. If I keep the same C, right, over here in the next one, you get the value of C as something different. So that looks odd, right? Even though they are integration constant, it's better to call them different integration constant, right? So that's your C1. Just replace it back. That's your F. S. Simplify where you can. Combine the terms so it looks less horrible. Rather than leaving it like this, I would combine it wherever I can. Okay. Good. So that was our first modeling question. Right. Now we go for the second modeling question. Right. So that was first question that we have solved. Now let's move to the second case, which we call the mixing problem. So it's like a physical and chemical solution. There's some salt and you are having some chemical inserted, all that kind of situation. So what happens, as you can see here, There is some initial volume, V0. Later, there is some M0 physical substance, could be salt or anything, at the time T0. That's the initial start. You are inserting some Q liters per minute of some salt water, something, right? Which has some mass M gram per liter. Right? It could be 5% alcohol solution, 5% salt solution. So in 1 liter, you got 5% of the salt, right? So there is some inflow. Since the capacity of the tank is fixed, there is an inflow. It will only sustain if there is an outflow. Simple logic, right? You cannot just keep pouring if there is no exit, if there is no outflow, right? So there is some inflow here, as you can see. That's an inflow, right? Some Q liter per minute solution M containing M gram per liter is being coming in, and there is an outflow Q liter per minute, right? Okay. I just have to warn you that it kind of is tricky. So if you don't understand, please get in touch with me. Yeah. Right. So there are a couple of steps that we will follow, right? Step number 1. So what we do, we establish a mathematical model for this one. Okay. Right. So what we do, S dash T, the change in the salt water content at time T, is obviously the inflow minus outflow. M in minus M out. Simple thing. Whatever you're inserting minus going out, right? M in, the brine inflow rate, right? What is the in part? What is incoming part, right? So brine inflow, that's like chemical cleaning process. So it's a brine inflow rate. So in short, inflow rate times by salt gram per liter in the brine, in the content, right? So we call it Q times M, inflow times the salt gram, right? The concentration of salt in the tank at any time is given by S by V0, right? That's a concentration. Okay, so what about the out part, right? We talked about in part, the out part. Brine outflow, similar to what you held here, and salt concentration in the tank, the outgoing, right? Incoming, we are talking about in the incoming mixture. For outgoing is whatever in the tank is goes out, right? So is Q times S over V0, okay? So if you talk about S dash, which was S dash is, as per the form, inflow, M in minus M out. Now you call it S dash or ds by dt. What is N? In is Q times M minus out, which is QS over V0, right? Whenever we are writing differential equation, we don't write that S is a function of T. So you call it S or S of T is the same thing, right? But you wouldn't prefer to write like this. Otherwise, you might get mistaken of S times T, right? So we just write it S, right? And we assume we know that S is a function of T, right? So we got our differential equation. ds by dt is equal to qm minus qs over v0. What do? We solve it. Okay, so we write it bit nicely. Step 2 is solving the mathematical model. So you got ds by dt, right? You can write it as ds by dt plus we got q over v0 s is equal to qm. Because our variable is s, we talk about ds by dt. This will be treated, this will be treated as our p and q. So you can follow the same approach which we done in the earlier part, like going for P and Q and then going for the mu is equal to e raised to minus P dt and solving it, and then go for the final solution as the same thing that we did here. I'll just go back a few slides just to make you aware. The same situation, yeah? So this part, what we did here, right? P and Q, and then you got a differential equation, go for the mu V of t, or in our case, it will be S of t, and then mu times C integration B over this part. The same thing you can do. Or if you want, let's to refresh our memory and to keep everything clear in the mind, I have a different approach here. So what I'm doing is I'm talking about the homogeneous and non-homogeneous part, which we did it in week 3 and 5 and all that thing, mostly week 2 and 3. Yeah. Right. So what we do, we talk about the other part. Okay. So homogeneous part. So what is the corresponding homogeneous equation? The corresponding homogeneous equation will be ds by dt plus q over v0 s is 0. With the homogeneous, we said the right hand side is equal to 0. And the auxiliary equation from it, remember s is a variable, right? So it's a first part, so r plus q over v0. Sorry, we don't write s here, q over v0, right? Therefore, r is equal to minus q over v0, right? And our homogeneous solution, right? Keep everything clear in your mind. If you need to refer to any literature, C times e raised to minus r. So q over v0 t, right? This is your homogeneous part solution. Once we are done the homogeneous part, then we go for the particular solution part. We call it SP. P indicates the particular solution, right? It's only constant on right hand side. So it's simply A, right? And therefore your SP dash is 0. We replace it in this equation, right? To find our A. So ds by dt plus q over v0 s is equal to mq. This is our equation. ds by dt or s dash is 0. q over v0 a is equal to mq. And therefore, your a will be minus, sorry, not minus, simply as it is, m v0. That's our a. We found a, therefore your SP is mv0. And finally, we used to call it SG, general solution, which is the homogeneous and the particular solution, right? Homogeneous, as we got it here, that was C e raised to minus Q over R, C e raised to minus Q over V0 T, and the particular, which is MV0. So this is your S. I'll write it again. C e raised to minus QT over V0 plus MV0. This is your S. Now, I just did some paperwork before I started the lecture just to make sure everything is right. And I followed the same approach of that P and Q approach, right? And you follow the same process, finding your mu of t, which would be e raised to minus at, or I called this constants a and b, and then going for your s of t, mu of t, c plus e raised to. So that all is verified, and that is the same answer which you have obtained here, right? But I just wanted to give you a different revision of the things we have done it earlier, right? Now, there is some integration constant here, right? But we have the initial condition when t was 0, your s is m0, the initial part, right? Which we'll replace here. So m0 is equal to mv0 plus t is 0. So this one, right? And therefore c is equal to m0 minus mv0, which we replace in our s. So s will be mv0 c, that is this, times by e raised to minus q over v0 t, right? Or you could have said qt over v0, right? That is your s. Now, if you want to simplify that a bit, combining your m0 and m and all that thing, so we simplify mv0, m0 e raised to minus qt over v0, mv0 e raised to minus qt over v0, and then we combine this mv0 term. So that will be mv0 1 minus e raised to qt over v0 plus m0 e raised to minus qt over v0. Right, so that's your final S. This is your final S. Okay. If we have to verify it, we quickly verify it. What happens when t is 0? Okay, when t is 0, what will happen? Right, S, right, which is mv0, 1 minus e raised to 0, and m0 e raised to 0. You simplified mv0 times 0, yep, because e power 0 is 1. So 1 minus 1 plus m0 e raised to 0, which is 1. Yeah. And so finally, your S becomes m0. And this makes sense, right? This is what we have it. When t is 0, S is m0, the initial concentration. Okay. Now, what happens when you let t really large? Because we don't know when solution will change. So we don't know a fixed t. But when we are talking about simulation, when we're talking about various scenario verification, we have to make sure that we are having the correct information, right? So when your t is infinite, really big t, you got abundance of time. What will happen then? So my S, which is mv0, right, plus m0 minus mv0 e raised to minus infinite. So e raised to minus infinite, which is 1 over e raised to infinity, 1 over extremely large number, and that will tend to be 0. And therefore, your S will be nothing but mv0. So when you got no restriction of time, your salt S, right, will be mv0. So long enough time, S is the amount of salt, which is the density of the fluid times by the capacity. V0 is the capacity, the volume of the tank, right? So if the time is not enough, the original salty water will be flushed out, right? But if you more than enough time, the whole water will be occupied with the salty water, right? When you got enough time, MV0 is the what you are getting, okay? Cool. We have this part here. This is from the earlier, when we are discussing about solution of differential equation, we talk about transient part and steady state part, right? Okay, so transient component is higher to start with, right? This is a bit higher, but as you have more time, right? Time passes, right? It is taken over by the steady state solution part, this part, right? And obviously when t goes to infinity, obviously this part, e raised to minus t times something, something, that will be 0, right? So this is 0, mv0, 1 times 1 minus 0, and therefore your S will be nothing but mv0, okay? Now, if we go for the simulation or validation of the mathematical part here, what will happen? So we got various situations here, right? We have our thing, m0 is 100, the initial part, the volume is 1000, m, right, which is 1, and q is 10, right? So v0 is 1000. The new fluid that we are inserting is 1 gram per liter. And the rate of insert, which is q, which is 10 liter per minute, right? So the final amount S is 10 liter per minute, right? That is what we have. So it started with 100, and then the dash line, as you can see, as the time increases, is slowly going out. And approximately over here, it's almost 0, right? So this is what this thing S1 is. With the S2, the new part, the upper dash line, this thing, right, is a fresh salt water, the new salt water. What happens here? This line, the upper dash line, right? What happens? At some point here, it almost, right, roughly into 3, and it's almost aligned. is almost on, as you can see here, right? They're almost the same, right? So fresh salt water, as the time passes, right, is increasing. So as you can see, the combined S is the combined one, right? Inflow minus outflow, the combined one, right? So 300 meter, as you can see, is occupied by the new salt water as the original or the old is flushing out. Okay. Right. But what if we have some different scenario, right? So this was the original part. As we know, around this time, it's almost, this is the original situation. We take a couple of various things. Over here, what we do, we keep M0 as 100, V0 is 1000, but we have the intake is 5, and this is 100 liter, right? If we change the parameter and have 100 gram to start with, right? And the inflow is 5 gram per liter, and the new fluid intake is 100 liter per minute, what's going to happen? It goes very quickly. So as you draw a line, if you try to, draw a line from here, almost somewhere here, which is roughly half, but a bit less. So around 40 minutes approximately, right? With the new parameter, the saltimeter has replaced, the new saltimeter has replaced the old one. And your combined S, as you can see, is almost, the new salt water, right? And as you can see, as we know that MV0, which is 5 times 1000, and that's why you got 5000 here, right? It's almost at the capacity. Right. Let's talk about one more, the middle dotted line. So what we do with the middle dotted line, M0 is 100, V0 is 1000, M is 5, but the intake rate is, so we are just changing the salt water content, but this line is the same, right? So it's another situation with a given parameter. So lower flush out rate, and almost, because it was 100, this is 1/10 of 100 because it's just 10, right? So it takes more time. As you can see, it even in 500 there is a bit of gap, so you have to go a bit further, maybe approximately around 600 minute, so 10 hours, it will be fleshed out, right? So this is the simulation part of the problem. Okay, we got one more part, that is a case 3. We'll solve it. Okay, let's go for this. Right. So in this case, we are talking about spraying a fruit tree with pesticides. Okay. In spraying a fruit tree with pesticides spray onto the tree. We call it X-gram. But as we know that not everything will be hold over there, right? Outflow to the soil with a certain rates per day. You don't want to put too much. You don't want to put less, right? And if you don't put anything, obviously there'll be a lot of, insects. So you won't have the same outcome or the yield of the fruits, right? Conversely, the pesticide in the soil, Y-gram, has a certain uptake rate into the tree per day, right? So assume the rate of change in both the tree and the soil. Again, on the tree is X, on this one is Y. It's given by this differential equation, dx by dt and dy by dt, whatever that is, 0.7x, 0.1581y, and the 3162x minus 0.3y. Find the pesticides in both tree and soil. So obviously, we are trying to find the values of x and y, right? Solving differential equation, in other words. Since there is 100-gram pesticide was initially sprayed, right, in which 200-gram fell on the soil during spring. So actually 1,000 minus 200. So that x, which when we replace the initial value, when t is 0, your x will be 800,000 minus 200. That's what your x will be, right? But again, we will talk about it when it comes to replacing the initial values, right? For now, let's focus on solving the differential equation. So the good thing here, the equations are formed for you. This is just an application of differential equation where we are solving this parametric differential equation we have dealt this, I think week 7 or 8 content where we are solving such, I think it was last week, could be the earlier week, where we are solving this type of differential equation, right? Okay. I put some typed material because then it was very clumsy to do everything. Okay. Right. So recall what we did here. So you've got a dx by dt, which contains some x, some y. We are eliminating. Always remember, why do we have to solve it like this? Right now, you've got 3 variables, x, y, and t. You've got only 2 sides when you're trying to integrate this with any of the method, because they are not partial differentiation. You can't take care of 3 variables. So you have to make an equation with 2 variables, preferably x or t or y and t, right? Because x is a function of t, y is a function of t. Earlier section, we had either y is a function of t, or x is a function of t, or y is a function of x. So again, you always have one dependent variable, one independent variable. Okay? Right, so what we do? We try to solve the equation. Okay, so your x, we replace this up here. So dy by dt, which we call y dash, right? Plus 0.3y, so it goes on the other side. If I solve this, we call it y dash plus 0.3y is 0.3162x, right? This is what's been done here. So you got your x, again, you divide by 0.3162, just divide by here. So you got your x, we call dy by dt or y dash. So you got your x equation as this, but we got dx by dt here, okay? So what we do, it's differentiation. So x dash or dx by dt. So this y dash becomes y double dash and y becomes y dash. So you got the value of x dash, you got the value of x. If you look at your first ODE, your x dash is minus 0.7x plus 1581y, right? You got your x dash and y value. What we do, we got x dash, x, we plug everything and the whole equation will be in form of y. Substitute x dash and x in the first ODE. So this is your x dash is equal to minus 0.7 times x and this. Simplify with all the multiplication of number, right? So this one is multiplied, this one is multiplied, right? So that's here. Then combine the y term. So you got 3.1626 y double dash, 162 y dash, and this. Now what we do, divide by 3.1626, and you got a nice, friendly second order linear ODE, homogeneous linear ODE, right? Once you get that, that's it. You got an equation in y double dash. We know how to solve it. It's homogeneous. We talk about the auxiliary part, r square, r, and 0.6. And then we go for 2 root. Since it's a fraction or decimal, it's reasonably to go for the quadratic formula, minus b plus or minus b square minus 4ac over 2a. You plug in your a, b, c. A is 1, b is 1, c is 0.6. You plug in, you got 2 r values. And since it's a homogeneous, simple stuff, c1 e raised to r1 t, c2 e raised to r2 t. Plug in all the values, you get your y. Now, in order to obtain our x, if you recall, x is having y dash and y. So we already got our y, but we go for y dash as well, right? So this is the differentiation, the y dash. Now the x is 3.6126 y dash and 9488y. You plug in the value of this, is again writing the same thing. You plug in the value of y dash and y here, right? And therefore you have some x equation. Perfect. So you got the y value, you got the x value. That's it. We are just writing it nicely here. Okay. Now, this is where the initial part comes as x is 800. As I explained earlier, I explained again. Since 1,000-gram pesticide was initially sprayed on a tree in which 200 fell, so actual amount on the tree, right, x, right, is sprayed on. So that will be 800. And of course, y, which is on the soil, which is 200. So you got your 800 and 200. You got two simultaneous linear equations. Either you go for substitution or elimination or any other forms, just solve it. You'll get your C1 and C2, right? Once you get your C1 and C2, use this C1 and C2 in here, and that's your X and Y. Okay, and if we have to verify that, whether it's right or whether we have fluffed anything, just try t is equal to 0. 186 plus 614, 800. 588 minus 388, 200, bang. Both of them are verified, right? So it's fine, it's perfect, okay? Cool, so we got your X and Y as an equation. Now the last part, okay? The last part, the graph of this. How would it look like? So when you wanted to graph this, I think there was a part. Yeah, I think it's coming up here. Oops, no, it's not. Okay, anyway, I'll draw it for you here. Doesn't matter. When you wanted to graph this, there are two parts, X and Y. So we have some different scale, 5, 10, 15, 20, and you keep going. This is a time in the day, right? And this is the pesticide in gram P in the gram, right? So I think you talk go 800, 100, 200, 3, 4, 5, 6, 7, 8. This is 800, 700, 600, 500, 400, 300, 200, and 100, right? So if you look at, you already got the value of X and Y. In order to plot, you will use your scientific calculator and plot it. Same for the Y, right? So first part will start at 800, right? And it will gradually decline. And gradually decline, it goes up to this 25 somewhere, and then it goes almost 0, right? With the Y, it should start with 200. Why? Because that's the initial value given. Goes at a peak, and after a certain point, again, it starts declining. This is how it looks like. How to draw this curve? As I told you, scientific calculator, or you can go for plugging the value in the Excel and just drawing a curve. Just write X is equal to this, Y is equal to this. You go for MS, Excel, or Google Sheet and just, take different values of X. It will plot a nice graph. We have done that in earlier sessions. If you still have any problem with that, always, get in touch. Yeah. So that's your X and Y values, right? Maybe we can run the Excel. Maybe we can run the Excel. Yeah, let's do it. Okay, so let's plug in the X value. So first of all, I'll write it here. So this is just me writing the X and Y value, 186. E, for times I'm writing like this, E power minus 0.2t plus 614 E power minus 0.8t, and again y of t. You don't have to, I'm just writing. Yeah? 588 times E. Okay, all of those things I can copy it and change it, right? Right, okay, so we got 588, and the other part is minus 388. Okay, now we wanted to construct this. Okay, so I will write t here, x and y. Okay, let's have t 0, 1, 2, and our slide had gone up to how much was it? We had gone up to 30. Okay, let's go for 30. So 0, 1, 2. You can select this to keep dragging. As you can see, it's moving, moving, moving. Great. Keep going. Go up to 30. Right? 30 is fine. Okay. Now X. How does it work? See how I type 186. See, when you write equal to, it will take as a formula, right? For exponential, we write exp, right? Minus 0.2 times the value of t, okay? Plus 614 times exp, right? Minus 0.8 times the value of t. That's your x value, and it's 800. Perfect. Okay. Similarly, I will type the value of y as well. Since I already typed it one, it's easier for me if I just use that pin, but we don't have 186. We got 588. It's not plus 614, it's minus 388, right? And the rest constants are the same. Just verifying it is the same. Yep, perfect. Okay, something wrong happened. What did we do? We didn't cancel the 614. So that's 200. So that verifies your 1,000 total. So that's 800 on X and 200, right? Now what you do, you select this two, either you double click and it will fill up everything. Okay, if you don't want it to do that, what you do is, go like this and keep it dropping, 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 dropping. Perfect. I just have to make sure that this one is good. Right. So it's declining here. That's perfect. Looks good. You have to be a bit careful when you type the formula. I think I missed a minus here, and that makes a big difference. That looks right. Yeah. So, because otherwise it's an increasing function, not a decreasing part. So first one verified because t is equal to 0. So whether your power is plus or minus doesn't really matter. So once you round this up, let's round this up to, sorry, yeah, this one down, right? And let's reduce the decimal, this one. That looks good. So we can see it's almost 0 and 1 in 30, this thing. And that's what we have it here when we were talking about it, right? It's almost like 25, 30, almost diminished, right? So your drawing or the numbers make sense. But let's plot it. So I'll just zoom out a bit. I will use this 3 and go to insert and let it choose the type on its own. Okay, how about this one? Right? Because that's what it got X and Y both. See, here is only Y, so it's not doing it properly. This one looks more cool, and the chart is here. And if you want, just expand this a bit, right? Have some data points, right? So you can right click on this one and say add data labels, right? See, this looks like this, so it's kind of verified. Same thing for here, add data line. And that's it. You got all the, if you think that's messy, just undo that thing. Okay, so that's your X label, that's your T and Y thing, right? So you have plotted this. Writing the formula up here helps me. So I'm not referring to some other literature. I got it here. Make sure. And when you click on that, you have to verify it. There is something called lock cell, but here I don't need to lock the cell, right? Lock cell is I put a dollar value so it doesn't move, right? If I was referring to some fixed value. Up here, T is 0, 1, 2, and it goes declining as we have done it like this. And almost here, see, almost at 25, you can't even see the blue line because that's very minimal. So in a scale of 100, from this 15, you're talking about 9, 10. From 20, you're talking about 3, 3, 2. So that's very negligible. And that's why you don't see the blue line here. Same thing with the orange, that's a Y value. After 20, it's all diminishing. So when you have drawn this one, they are almost like gone, right? Because you're talking about scale of 100. Cool. So this is how you plot them on the Excel, and then you can make it very fancy. I mean, just FYI, you can call it what? Fruit problem. Yeah, that's done. If you want, you can just go for this or go for format. And, I have something here. You can go for color, if you want any changes, or go here, go for right click, and you can really, really do a lot of fancy things here. When you right click, it says fill, and go for a fill, some light color, so looks more clear. You don't need the grid line. If you want it, just do undo if you want to keep the grid line. Okay. Right. So thank you very much. That's it for today. I will see you next week. Next week, 10 and 11, we'll be talking about assignment 3, bit of discussion about assignment 3. So this covers all the required content for the whole unit. We got week 10 and 11, where we'll be talking about 2 parts of assignment 3, which is 10 marks for the assignment 3. So assignment 1, 25 marks, assignment 2, 25 marks, assignment 3, 10 marks. So together it is 60 marks in the assignment, and the final exam for 14 marks. Okay. More details that will follow in the upcoming weeks. Thank you very much. And please reach out if you got any queries. Thank you.